All right, good morning, everybody. Let me go ahead, let me start my timer here so I stay on track and I'll try to get done with this. What I'd like to do today then is we're going to finish up with our discussion of the differential rate law, and I wanted to say a couple last things about it after we finish up this problem here, which we started. Let me go ahead and share my screen with you, which we started yesterday. And so I want to go ahead and finish up with that, and then I will introduce to you the first of the integrated rate laws. Then it's the first order integrated rate law, and then that way then we can get started with that. And like I mentioned to you when I introduced kinetics, I think the integrated rate law is probably the more useful. I mean, both are useful. Again, it depends on the information that we were given about the experiment themselves. That will basically determine which one of the rate laws we use. But like I said, the integrated rate law is the one that I like using more. It's more commonly used. We use it also when we talk about the nuclear reactions, and we're going to see that. And it's just easier to look at the information and determine then the order of the reaction. Now, obviously, with differential rate laws, this is pretty simple too. It's not that difficult, and we saw that. But with the differential rate law, you have to make sure you understand then that we use this when we are given rates and when we are given, let me go ahead and do the annotate, and when we're given concentrations. Okay, so that's what you have to notice here. So if you notice here, what we solved, what we worked out yesterday is then we were able to determine then the order, for each one of the reactants here. And then from that, then we were able to add it up and get the overall order number for this reaction. But in order to get that, what we saw, what we had to do then is we had to take 4 different experiments, and if actually you were to run this reaction in lab, you would probably run this reaction maybe a couple more times. 4 may not be enough, but you'd run this reaction and just to make sure that these concentrations here and the rates that you measure here are somewhat consistent. Okay? But again, these rates here, remember, you can obtain this from graphing the data of time versus concentration, and that's where we get the rates here. Okay. All right. So so with that said, if you notice, then what we need then is we need then the concentrations, and then we need the rates here. Okay. And so once we have that, we can determine then the order of this reaction here. All right. So we were able to do that. Let me go ahead and open up a second screen here. Let me open up a whiteboard. And let's talk about the second part of it. So we were able to determine then that the overall reaction order here was a 4th order reaction. Okay, let's go ahead then and let's write that down and let's see how we obtain it. Okay, so hopefully have this in front of you. This is number 1 from your problems that we did this morning. Okay, and let me go ahead and let's write that down, because the second part of this problem here asks us to find then the rate constant itself. And like I pointed out to you, I pointed this out to you when we started the differential rate law. Getting the constant ends up being pretty simple. The hardest part then is the harder of the two is getting the order number. The constant then is a matter of just plugging in the values and getting the constant itself. Okay, so with that said, then the rate law for this particular reaction, then it's going to be the rate is going to be equal to the concentration, K, times the concentration of bromate, and this is to the first power, 8 times the concentration of bromide, also to the first power, times the concentration of hydrogen raised to the second power. So that is the rate law for this particular reaction. Okay? Now, solving for K then, folks, trying to find the rate constant then becomes very simple. What we're going to do is we're going to go ahead and divide both sides by the different concentrations here. And remember, these concentrations then are the concentrations towards the beginning of this reaction. We want these here, we want to address these before then equilibrium starts. Okay. All right, so at this point then, we're just going to pick any one of those experiments. I'm just going to arbitrarily pick the first experiment and plug in the numbers. Okay, so the rate for the first experiment then is going to be 8.0 times 10 to the minus 4, and the units are molarity per, I think, seconds here. Yeah, so molarities per second. Right, so that's going to be over now. the concentrations that accompany this particular reaction. So in experiment 1, the concentration of bromate was 0.01 molar. So it's I'm sorry, 0.10 molar. Concentration of bromide was also 0.10 molar. Okay, and then finally, the concentration of hydrogen ion was also 0.10 molar, and we're going to square that right there. All right, so you plug all those numbers in. I end up getting, please make sure you check this for me. I get 8.0. Okay, so I get 8.0, and the unit's going to end up being then liters cubed, and you please you do this. Okay, so it's going to be liters cubed over mole cubed times seconds. Okay. All right, so that is how we find the constant for this particular reaction here. That is the rate constant for this particular reaction. Okay, and you can again, you can plug in. So I chose to use the values for experiment 1 here. So I took the values from experiment number 1. You can go ahead and plug in any value from any of the other 3 experiments, and you should get or close within a tenth or even closer value here, and you should get the same constant, because this represents, and the constant then represents, it should be the same for all the experiments. Okay? All right. And again, I just want to point out to you then the 1 to 1 to 2 does not correspond to the balanced chemical equation. Remember, the coefficients for the balanced chemical equation gives us the stoichiometry of the reaction, not necessarily how fast or the rate of the reaction itself. Okay. All right, very good. So let's go ahead then, and if there are any questions about the differential rate, well, that's it. That's it for the differential rate law. That's all that I would like you to know about the differential rate law. And so with that said, then let's go ahead then and let's move on. Okay, so let me go ahead and close up the screen here, and let's move on and let's talk about then the integrated rate law. Okay, and so if you have any questions, like I said, please come by. Or stick around, or come by. I will be available today until about 11 o'clock. I have a meeting afterwards. So please come by. As you're watching this video here, if you need to pause it to come see me, make sure you come see me. Okay? Or once you get done with this video, this lesson here, come by and see me and get the questions answered. If not, I will be available tomorrow after my 7th grade class to help you with this material as well. Okay. All right. So with that said, let's talk about the integrated rate laws then. Okay. Now, for those of you who have had calculus, with the differential rate law, we refer to it as the differential rate law because actually we were taking we were using differentials in order to get those. The differential then employs then the change in the concentration which you have there over the change in time. We can write it as d concentration of the reactant over d time. Okay, and that's why we refer to it as the differential rate law. The integrated rate law is also a calculus term. So what we can do then is we can take the differential rate law, integrate it. And again, if you folks are interested in doing that, please come by and see me. I think it'd be informative for you to see how that's done. For those of you who have had calculus or are taking calculus, come by and I will derive the integrated rate law for you. And then again, like I said, it's very informative for you. In my opinion, I always feel like, if you understand how a formula is derived or how it comes about to be the way it is, it's just always easier and it's helpful to understand the equation and also then to use it. Okay, so we don't have class time for me to integrate it for you, but please make sure you understand that. Okay, so we saw the differential rate law for this reaction. This is the first order reaction. We already saw this already at the very beginning of this chapter here. I did it for you. And so let's go ahead and let's take a look at that differential rate law there. Okay, so there it is. It's first order. It's a first order reaction because then the n here is going to be 1. Okay. Now, for this particular reaction here, for this particular law here, okay, You would use the differential rate law here if you had information about the rate, which is what we just saw in the previous experiment. If you can obtain information about the rate, and if you know the concentrations, then you can use the differential rate law, say, to find K. And so this is useful then to predict other rates. Once you have the rate constant here, K, you can predict the rates at other concentrations. That's why these rate laws work for us. Okay? Or conversely, if you know the rate, you can predict the concentration at that particular rate. Okay, as long as you know this rate constant here, that is doable. Okay, all right. However, there are experiments and quite a few experiments where we don't have the values for the rate. Okay, but we want to be able to still determine how quickly the concentration will change as a result of a change in time. Okay, and so what we can do then is if we integrate this, so we're going to apply math to this here. We're going to apply calculus to this. And if we integrate this here, and again, this is not quite set up the way that a differential rate law will be. You would typically see then the delta here be replaced by the a little d that represents the my mind isn't working. It's not in calculus now, but but we would see then the differentials here instead. Okay, this would be a first derivative. So you'd see d here instead of any other symbol. So you'd have the first derivative as it applies to time. That is the change in the concentration of dinitrous pentoxide as a function of time. But anyway, with that said, then if you integrate it that way, then you will get this particular equation right here. Okay. Now, for those of you who have not had calculus, you can still use this. It's just much harder to see how is it that you get from this reaction here, which is K times the concentration of dinitrous pentoxide. How do you get that to natural log? Okay, and that is confusing. But like I said, for those of you who have had calculus, if you want to see how we integrate to get that, it would be very informative for you. But again, you don't need the calculus. You don't need the calculus to understand this. This course was not billed as a class that needs that you require calculus. You do need algebra in order to get this done. But like I said, you don't need to know how we get from the top equation here, which is the differential rate law, to the integrated rate law here. And these two are in rate laws for first order reactions. Okay, for first order reactions here. So this is the format right here of a reaction. This is the integrated rate law for a reaction that is first order in nature. Okay, right. So let's go ahead then and let's take a look at this. So this is the general. So let's say then that this is the general reaction here. We have then reactant A go to products. Now, mind you, this is a rate law, so we are still looking at concentrations of reactants, okay? And we're still looking at the concentration of the reactants at the early stages of the reaction. We do not want the reaction to reach equilibrium. Okay, so with this integrated rate law here, then what you're going to see then, this particular integrated rate law here, this is first order as well. Okay, and this is the format that you will see it in. And what you're going to see then is that this first order rate law gives us quite a bit of information. But if you notice here, this is the concentration at some final time. This is concentration at initial time. That's what concentration A naught represents. K is going to be then the equilibrium constant, the same equilibrium constant here, and T is for time. Okay, so this is you can think of A here on the left-hand side as final concentration at a time interval that is not at the start, that is not zero. K is going to be the rate constant. T then is the time interval we were taking a look at, and A initial then is the concentration right when we start this particular time interval here. Okay, so that's what we have then for the integrated rate law. Now, this integrated rate law, if you notice, then there's a few other things that you'll notice about this integrated rate law. First of all, if you take a look at this is actually written in the equation of the slope-intercept formula here. This is slope-intercept, which means then if we recognize the slope-intercept, this term on the left-hand side represents the y, okay, the y function. This is going to be then K is going to be the slope. T here is going to be the x function, and this is going to be then the y-intercept. The natural log of A naught is going to be your y-intercept, which means then when we plot this, you can imagine then that we're going to be plotting the natural log. We'll be plotting the natural log of concentration, okay, versus time. Okay, so when we plot this, we should get a straight line when we get that. So the cool thing about this, okay, and let me go ahead and let me share this with you on the side. Okay? So if you notice, if you recognize that, if you plot this, these data points here, okay, so if you collect the data points here along the x-axis and along the y-axis here, okay, what we will be plotting then is time here, and then natural log of a on the y-axis. That means then if we get a straight line, okay, if we get a straight line when we plot it in this manner here, and this is what makes this so cool and so easy to use. When we plot this here and we get a straight line, when we plot these points here, that straight line, okay, represents then, as soon as you see that, it will be a first order reaction. And that's it. That's it. That's why I like using this, because it's so simple. And yes, you got to do a little bit of plotting. Okay, you have to plot a little bit, but I think it's much more visual. It's much more visual than the differential rate law. Okay, so you take your data points, okay, you take what you have, you take the natural log of it, you graph it, you put it on paper, and then if there's a line of best fit, a straight line that goes through all those data points, you have right there on your hands a reaction that is a first order reaction. Okay, and so that's really going to be useful. And what we'll do then is in just a moment, I'll demonstrate that to you. But if you notice here, we can rearrange this equation as well to solve it a little bit more simply. But this also, and again, since we're so strapped for time, if you're interested in seeing how we get from this boxed equation here down to this equation here, come by and see me, and I will show you that. Okay, but what I'd like to do then is I would like to go ahead and I would like to demonstrate for you how we by plotting the information, we can determine then the rate of the equation itself. Okay, so let's go ahead then and let's take a look at an example here, example problem. Okay, all right. So here we have some data points. Okay, so if you notice here, we're not going to use the differential rate law. We can't use the differential rate law in order to get this done. Okay, now you can go ahead and you can solve for the rate here. Just get the change in the dinitrogen pentoxide concentration over change in time. So you'd have to calculate for the rate. Once you have that rate, then you got to calculate for enough rates here, and then you got to run the experiment over again. You got to run the experiment a couple times, varying the concentration here just a little bit, okay, and then seeing then what the relationship is between the change in concentration and the change in time, okay, and the change in the rate. Okay, but then again, if you want to do it that way, you're more than welcome to do so. But there's an easier way to do that. Okay, if we use the integrated rate law here, and this is what I want you to recognize here. If we use the integrated rate law here, we can go ahead then and we just using this information here, which is the concentration, and there is time, okay, and then we plot it, we should be able to find then the value, what order this reaction is. So again, we already know what this the order of this reaction is, but I want to use this to help you see this. Okay, so what we want to do then is first thing we want to do is we want to take these concentrations here. We want to take all these concentrations here. And we want to take the natural log. So take the natural log of all of these concentrations. We're going to go ahead and do that first, and I'll do that for you in just a moment. Okay. And then what we're going to do then is we're going to take all of that and we're going to plot it. So this is going to be all those points then will be data points along the y-axis, and time then is going to be all the data points along the x-axis, and then we're going to plot each one of these points. And then if we get a straight line, we have on our hands this we have confirmation then that this is a first order reaction. Okay, so let's go ahead then. Let's verify that this is first order using integration and the integrated rate law. We're not going to use differential rate law. Okay, and then we'll go ahead and calculate for the constant. That's going to be pretty straightforward. Okay, so let's go ahead then. All right, so I'm going to go ahead and I did this for you already. Okay, so I took the natural log of all these. Okay, so let's go ahead and do that. So there it is. I've taken the natural log of all those values, and there it is. These are the values for the natural log of these concentrations here. Okay, so that's what we did, and there's the time. Then what I did was that I plotted for you the points here. So each one of these points here. So for example, this point right here. Let me go ahead and do this for you. This point right here. Oh, sorry, where's my? Oh, sorry. Back. Okay. This point right here. corresponds to these two data points right there. Okay, so roughly about negative 2303 at 0. So this point right here has the coordinates of 0, negative 2.303. And you can see that all these other points correspond to these here. We can draw a line through all those points. Now, in real, when we actually run these experiments, the data points will not fit perfectly on the line here. But if they come close, this provides confirmation right there. This straight line right there, when you plot and understand, this is going to be key. In order to confirm that this is a first order reaction, we have to plot the natural log of the concentrations versus time. And that's why I created this table for you. All these values here represents the natural log. And what we do then with that is we plot it along the, the y-axis. There they are. And then if you notice with time, what did we do? We plotted it along the x-axis. Okay. So we do that, we put it in the plot, and this straight line here, that is confirmation of first order reaction. This is first order kinetics. Okay. And that is our confirmation. That is the extent of the math that we had to do, folks. Take the natural log of those concentrations. Now, folks, you got to find the natural log key on your calculator, okay? Because if you don't have that natural log key in your calculator, then you're going to be at a disadvantage here. Okay, so this is the reason why the integrated rate law is so much easier to use. And for me, like I said, I choose when I did these experiments here, I chose to use the integrated rate laws to confirm when I needed to the kinetics of the reaction. Okay. All right. So with that said, then no need to calculate for the rate, okay? Because we don't need to. We can just plot this and get that information directly. Okay. All right. So with that said, okay, how then can we solve then for and with the second half of the question then asked then to calculate for the rate constant? Okay, how do we get that? Well, if you understood, and let's go ahead and write this out here. We had the integrated rate laws written out in. Let me go ahead and write that out for you. The integrated rate law here, and let me go ahead and do this here, was the natural log of the concentration. And this is going to be minus KT plus the natural log of A initial. Okay. K, folks, the equilibrium constant. If you recognize it, again, this is the slope. This is the slope-intercept form. K is the slope of that line. So to find K, then all we have to do then is pick 2 points on the line here. Pick 2 points on the line, and I'm just going to go ahead and arbitrarily pick this point here and the last point all the way down here. Just make it simple for myself. Okay, so the coordinates down here then are going to be 400 and 400 seconds and negative 5.075. Okay, and so using those 2 points, all we were going to do then is find the slope of this line. Okay, so let's go ahead and then find the slope of this line. Then it's going to be y over x. It's going to be a negative 5.075, okay, minus a negative 2.303, okay, all over 400 seconds minus 0 seconds. And again, you calculate for that, I end up with an answer then that is negative 6.93 times 10 to the minus 3. And the units then are going to be inverse seconds. That is your slope, but that is also your value for K. And that's how we obtain then the equilibrium constant. And so this equilibrium constant is the exact same equilibrium constant as we saw in the differential rate equation. Okay. It has to be the same. It's a constant. So regardless of whether the K is a part of the integrated rate law here, or whether K is the part of the difference rate law, K has to be the same. And again, that's the reason why seeing how we integrate this reaction here is going to make it, it's going to help you better understand how to use the integrated rate law and what it's used for. Okay. All right. So let me go ahead then, and I'm going to ask you to let's go ahead and let's take a look at number 2 here. Okay. Now, with that said, in number 2 here, using the data that we collected in the sample problem that I just did for you, we want to now calculate. So this is what the rate laws do for us. Okay. So in this case, then we don't need to collect any more data. We don't need to collect any more data. Now that we know what K is, now that we know that this is a first order reaction, okay, what we can do then is we can go ahead and then we can find at 150 seconds. And again, here, if you notice here, the time here, we did not collect the data at 150 seconds. We recorded the concentration at 50, at 100, 200, 300, but not 150 seconds. But that's not going to be a problem because using the integrated rate law here, and the reason why we're going to use the integrated rate law is because, again, we don't have rates. Okay, so let's go ahead and write down that integrated rate law again. Okay, and again, understand now we know what K is, so it's going to be the natural log of the concentration minus Kt plus natural log of the concentration initial, excuse me. All right. All right. So with that said, what I'd like you to do is we want to find then, we want to find this concentration right there. Okay, we want to find that concentration right there. Take about a couple minutes to work that out, and then we'll go over it together. Okay, so take a couple minutes, work that out, and let's see what you come up with. Okay, so and then we'll compare answers. Okay, 2 minutes. All right, folks. Let me go ahead then, and let me open up a whiteboard here, and let's work through this. Okay, take a look at what you did, and let's compare what we have. Let's compare our answers right here. Okay, so. Writing down then the integrated rate law here, we have then natural log of A. It's going to be equal to minus Kt plus the concentration, natural log of the initial concentration. Okay. All right. Let's go ahead then and let's plug in the values here. So let me just write this down here. K was negative, I think, let me look at this, negative 6.93, negative 6.93 times 10 to the minus 3 inverse seconds. Okay. The time that they want us to examine then is 150 seconds here. An A initial is going to be a concentration of A at 0 seconds, and that's going to be 0.100 molar, right? And so let's go ahead then and let's solve for A here. Okay. Now, in order to solve for A, then we got to be careful here. We got to take the inverse natural log, which is going to be Euler's number. Okay, so it's going to be the base E. Okay, so let's go ahead and do that, and make sure you keep that in mind. But I'm going to substitute in the values here to help us with that. Okay, so the concentration of A then is going to be then let's do this. E raised to the power of minus Kt plus natural log of, okay, so that's what we have right there. If you're not quite sure how we got from that step to this step, okay, please make sure you come by and see me. That's just a quick, simple review. But I think you learn about Euler's number in, what, I don't know, pre-calculus maybe earlier, algebra 2. I don't remember, but if you don't remember that, please make sure you come by and see me. Okay. All right. So with that said, then, let's go ahead then and let's plug in those values. E to the minus 6.93 times 10 to the minus third, okay, times 150 seconds plus natural log of 0.1000. Okay. All right, so remember, this is going to be 2.7, like 1828, and it keeps repeating to a certain decimal point. So, but let your calculator do the work there. Okay, I end up with a value that is 0.0353 molar. Okay, so that is the concentration of the reaction at 150 seconds. Okay, that's the concentration of nitrogen, dinitrogen pentoxide. I'm sorry, I put A in there, but that should be dinitrogen pentoxide. And so that's what we have. Okay. Now, you remember there was that alternative reaction, that alternative form of the equation that you can use, and that's what we have then is the natural log of, and let me just make sure I got this right, natural log of A initial over A is going to be equal to K T. Okay. You can use this as well. Okay. Now I'll let you go ahead and plug it. It's not going to be any different, but you can go ahead and plug it in and use that as well. It's just a little bit easier. I would probably go in that direction and use that equation instead. But go ahead and plug that in and confirm then that you would, should get the same answer as you get right here. Okay, so that's what we have then for our answer. Okay. All right. Now there is a so let me go ahead and save that for you. Okay. But let's go ahead and let's take a look at something else here I want to point out to you. Okay. Go back to this problem here. Okay, so there is an even easier way to determine the order of the reaction using the integrated rate law here. And let me see. I think we can get started with this. Okay, and I want to draw your attention to something. So again, we can use an integrated rate law here. Then again, we can take the natural log of all these here and plot it against these. Okay, but there is a simpler way. First of all, I want to ask you to consider something here. Okay, so let's consider what happens. So right here, for how long it takes for the concentration, the initial concentration here of dinitrogen pentoxide to be cut in half. Okay. All right. So we take a look at that. So in order, it takes about 100 seconds. So from the initial time to the time the concentration is cut in half, the time here is about 100 seconds. So I'm actually going to refer to this then as T1/2 because this represents the amount of time that we lose half of the concentration. Okay. Now let's take a look at then the amount of time that it takes to take half of this. So another halving event. Okay. So not having, but halving. Okay, which means then how much time does it take now for this to get cut in half? So from here to here. Okay, so if you notice here, then taking half of what's left over here. That's again, we're reducing it by a half. Okay, so we take the initial concentration, we determine how much time it takes to for that to be reduced in half, and now with what we have left over, how much more time does it take, or how much time does it take for that one to be cut in half? So the halving of this is also 100 seconds. So in the next 100 seconds, okay, you get another halving event. Okay, and so we can do that for the third one right here. So taking half of 0.025. Okay, so we reduce the concentration then by another half. Okay, and I'm sorry, where am I going with it? Yeah, another half, which is going to take us to 0.125. Okay, so if we cut the concentration in half again, it takes another 100 seconds. Okay? And so if you notice here, folks, okay, each halving event, okay, each time the concentration gets reduced in half. Okay, so this is the concentration being reduced by 1/2. That's what I refer to as the halving event here. Okay, so the time it takes to cut the concentration in half is the same for each one of these here. If you notice here, so the first halving event, 100 seconds. The second halving event, another 100 seconds. The third halving event is another 100 seconds. Okay, so if you notice here, it takes the same time interval to cut the concentration in half each time. If you see this, okay, that the half-life, and we refer to this then as the half-life concentration time, half-life concentration time. Okay. If you see that, you know then that this reaction, whatever the reaction may be, is going to be a first order reaction. Okay. This is what the integrated rate law, this is what we can do with the integrated rate law. And I'm going to show you, and I'm running low on time here, but in the lesson tomorrow, I'm going to show you how, and this one I will derive for you. This is how, this one I want to derive for you because it is really important that you're able to see this. Okay? But from the integrated rate law, we can show, we can give you an equation, we can derive an equation that will give us a first order rate reaction, a first order rate for a reaction. Okay? Now, we can do it empirically. We can do it, just analyze the numbers here like I did it. And oftentimes this actually is the faster way to go. Okay, don't use the equation that I'll derive for you tomorrow. Okay, but this is a faster way to go. And it's so easy to see this, the pattern that is there. Okay, so on tomorrow, then what I'm going to do is I'm going to continue this discussion. We're going to start with this here. But I really want you to make sure you see then that using the integrated rate law is so easy to identify the orders of the reactions, especially first order, second order, and what we refer to as zeroth order reactions. We'll talk about all those in the next couple days. Okay. All right, very good, folks. Have a good rest of your day. Come by and see me if you have any questions about this. And if not, I will see you folks tomorrow. I'll see you folks tomorrow. Okay. All right. Have a good rest of your day, folks, and I will see you. Bye.